My name is João Antonangelo. I am from Brazil. I did my bachelor's and master's in Brazil in agriculture engineering. My master's was focused on soil chemistry and soil fertility. As you know, most of the soils in Brazil, they are very old, very acidic. So work with lime application was always there for me to do something. Um, then I came to the US 7.5 years ago to do my PhD at Oklahoma State University. Completed my PhD 2019, did my postdoc there until 2022, where I also worked with biochar as a metal immobilization, with a metal immobilization approach, and also to see the lime effect of biochar in acidic soils. Then I moved to Tennessee as assistant professor of soil science with 100% teaching appointment, Austin Peay State University. But when I was doing my job at APSU, I found this job at Washington State University with more research than teaching, which is more my profile. Work to try to, most part of my research work that was in the job description was to handle soil acidity for farmers and growers here in Washington and Pacific Northwest, and try to understand better soil organic carbon dynamics. So I thought it was a very good fit with my career profile, and then I applied, and here I am.
So why don't we just start out with kind of what affects soil pH and what would be like the ideal soil pH for a no-tiller?
One of them, like it's a natural thing, is like the decomposition of organic matter. Okay, when you have the organic matter, it's going to be dissociated in organic anion and hydrogen plus. So that hydrogen plus is going to be able to acidify the medium, because the higher the concentration of hydrogen in the soil solution, the lower is the pH, the more acidic is the medium, right? So the second one is rainfall, water. Water, when it comes in contact with CO2 in the soil, it's going to form carbonic acid that's going to be dissociated, and in the dissociation reaction, it's going to release hydrogen plus to the soil solution. So whatever is releasing hydrogen plus to the soil solution is acidifying the medium. Okay, and in the soil, it's even more important because the partial pressure of CO2 in the soil is much higher than in the atmosphere, because microbes, they are respiring all the time. So if I am improving the CO2 concentration in the soil, I'm favoring the equation to the right side. So I'm acidifying the medium even more. And the other one, it's not natural, is the over-application of nitrogen fertilizer or nitrogen mineralization from organic matter. So we have ammonium. If you have ammonium as a source of inorganic nitrogen fertilizer or organic nitrogen fertilizer, very quickly it's going to become nitrate during the nitrification process. It's an oxidation process. So from ammonium to nitrate, it's going to release 4 hydrogen plus to the soil solution. That's going to acidify the medium very, very much. And when nitrogen is mineralized from the organic matter, it's also mineralized in the form of ammonium that's going to go through the oxidation process to become nitrate and release in hydrogen plus to the soil solution. So that's the main issue of soil acidification here in the US, and more specifically here where I'm working now, Washington and Pacific Northwest. While the other two that are more natural, it's the main issue in tropical soils, where rainfall and hot weather, they were there since the very beginning. So soils are more naturally acidified, very old soils.
So what are then like the consequences of having soil that's too acidic?
Okay, so one of the consequences, like dropping the pH, it's going to jeopardize the crops yield, because crops, they can only grow well at certain pH ranges, right? Here, what I'm trying to show you is that, for example, when using like nitrogen fertilizer, it's more like the consequence of soil acidification where we are right now. We can see that the ongoing application is dropping the pH regardless of the rate of nitrogen that's being applied. And of course, it's drastic when you have like very excessive rates of nitrogen application, for example, 240 pounds per acre. We can see that the ongoing application in the long term is dropping the pH a lot. And for example, for grains of winter wheat, it's very impactful. Like those excessive rates, like 120 and 240, they are dropping the pH a lot, as you can see, and the yields of the grain of winter wheat, they are dropping a lot as well. However, adequate rates like 30 and 60 pounds per acre is not dropping the pH too much, and it's giving us the best yields, if you can say that.
Yeah.
Yeah.
So does acidic soil, can it affect the efficiency of like herbicides and insecticides?
Oh, yes. There is this as well. So see, a rule of thumb is that like this range here, can you see the range?
Yes.
So it's like it's lightly acidic to close to neutral, 6 to 7. It's where we are gonna have like the highest level of availability for all plant available nutrients, but they are not only plant available nutrients, they are also they are available to other living beings like earthworms, insects that are good to the soil health, microorganisms that are good to the soil health. So in addition to the plant factor that can benefit from that pH because nutrients are going to become more available, we also have conveniently that range is very good for the reactions and metabolism of microbes, of pesticides for them to work at their optimum, and herbicides as well. We don't want to go too low in the pH or too high in the pH for pesticides and herbicides.
Okay.
And it's also where aluminum is no longer. So it's good for practically everything.
Okay, awesome. So with nitrogen application, is it like a compounding effect every year that it just creates more acidity in the soil?
Oh, yeah. So it's being applied like here. I use as an example here, Washington or Pacific Northwest. 40 years of application on average, 40 to 60 years. So since there is still no adequate soil test for nitrogen recommendation, what farmers do, they just keep applying nitrogen based on yield goal. Okay, so every single year then they're going to apply an amount that is based on yield goal that was previously calibrated by the university or other private labs around. So that ongoing application maybe is giving them like very good yields, but it's also acidifying the medium, and if they can neutralize that pH, they could get even better yields.
Mm-hmm. Okay. Is there anything that no-tillers can do to mitigate soil acidification besides going straight to lime applications?
So those are not only for no-till, but also for conventional tillage systems. If you cannot use lime because it's too expensive, or it's not efficient, or it's not available for you for some reason, you can try like cheaper options that are going to alleviate the problem in the short term, but they are not going to be as efficient as lime application because of the chemical reactions. So this one, like applying lime, it's a long-term effect because you are also impacting the reserve acidity, not only the acidity that is in the soil solution. We are also affecting when you are applying lime based on lime requirements from your soil test report. We are also impacting the reserve acidity, the acidity that is there to keep replenishing the soil solution if something goes wrong for them, like applying an alkaline material. So that's why applying lime is a long-term solution. But the other ones that are short-term solution, it's bait phosphate fertilizer with seeds to tie up active aluminum, and active aluminum is very toxic for plants. And another one is plant cultivars or varieties that are tolerant to aluminum toxicity or to low pH. As an example that I can show you here is, and there is also gypsum.
Okay.
Let me show you. So when you are trying to reduce like aluminum toxicity without applying a lime, we can do that by applying phosphorus, by baiting phosphorus when we are sowing the crop or something. Because even at low pH, when aluminum is more available, we can precipitate those free aluminum ions with phosphate, because the complexation and the affinity for those two ions is very, very strong. So we can see here like that you can form those complexes that are going to precipitate aluminum. But can you see that it's just a short-term goal, because it's not going to change the soil pH actually.
Mm-hmm.
It's just going to reduce aluminum toxicity because it's forming those complexes that are going to be precipitated. But the good thing is that you can do that even at low soil pH. Like this picture here is showing you, like on the left side, pH is 4.6. Aluminum is there available. There is no phosphorus applied. On the right side, for the same pH, the same soil, phosphorus was applied, like baiting phosphate with the seeds and everything. It was able to tie up aluminum even at low pH. And then the crop could grow very, very well, or much better. Okay, so gypsum is another way you can do that. It's much cheaper than lime, right?
Mm-hmm.
And it's much more soluble as well. I mean, it's gonna dissolve quickly. Okay, you can apply in the like as a short strategy, like 1 month or 15 days before sowing the crop. While lime, you would have to apply like 3 months ahead of time. But what gypsum does, it's going to be dissociated in calcium and sulfate. Okay, and then sulfate we move down because it's very soluble, it's very mobile in the soil. Okay, and it's going to precipitate aluminum. The same way phosphate was precipitating and reducing aluminum toxicity, sulfate will do the same. Okay, as an example here, I'm not showing you that gypsum is changing soil pH. I'm just showing you that root systems, they can grow better when the pH is a little bit higher, right? It's a little bit higher because aluminum was precipitated before, okay? Before it was suffering hydrolysis and making more hydrogen ions available to acidify the soil. So that is a way for us to precipitate aluminum as well. But again, it does not going to neutralize the soil acidity. It's not going to change the soil pH. Okay, and the other one is when you use like cultivars that are tolerant or resistant to aluminum acidity. Let me show you again. When we have like acidic soil, okay, pH 4.5 or 5.1, we can plant in that soil. Can you see the pictures, right?
Yes.
So for that soil with low pH, if you like, we are planting here like winter wheat, for example. So some where you can see something growing, something that is green, it means that that cultivar is low pH resistant or aluminum resistant. So it's another way to to try to overcome the acidity problem. Here is a difference when a soil is very acidic with aluminum. You can see that for the left side, like cultivars that are resistant to aluminum, the root system can grow actually, while the other that's very sensitive, it cannot grow, unfortunately.
Okay, so these crops that you're showing here, they grow hybrids that are specifically resistant to aluminum?
Yes. Okay. Yes, that's right. Yeah. Some cultivars that are developed for that region. Here, it's not Pacific Northwest. The last figures that I showed you, they were from the southern U.S.
Okay.
Yes.
Good. So then when we're talking about lime then, what does lime application actually do for the soil?
Okay, when we apply lime, can you see the screen? The
yes.
Lime, or lime. Okay, when we apply lime is basically this white powder material, right? That's basically composed of calcium carbonate. Calcium carbonate is going to be the component that's going to do the magic, okay? I mean, as I told you, it's not that soluble in comparison to gypsum. The solubility actually is very, very low. But that's why we have to apply like 3 months ahead of time in order to give it time to react in the soil and everything, with the soil moisture and everything. But when it reacts, it's going to be dissolved in calcium and carbonate. And carbonate is going to be the guy directly responsible to neutralize the soil acidity. So when it reacts with water, it's going to form bicarbonate, and in that process, it's going to release hydroxyls to the soil solution. And it's going to react one more time to release another hydroxyl to the soil solution. Which means hydroxyls, they are the opposite of soil acidity. They indicate alkalinity, right? So when they are formed in the soil solution, they are going to react with that hydrogen plus that was making the environment the soil system very acidic. And so they are going to neutralize by forming water, okay? So OH minus plus hydrogen forms water. So that's how lime neutralizes soil acidity. But what about calcium? Calcium, we are changing the calcium equilibrium in the soil solution because we are adding it externally, right? By applying lime. By changing the equilibrium, calcium is going to replace the hydrogen ions that were in the solid portion of the soil, the hydrogen ions that were in the reserve acidity. Okay, so in those hydrogen ions, they will move into the soil solution to be neutralized by the hydroxyls that were produced with the lime reaction. It's going to do the same thing with aluminum, but just for you to understand, like aluminum solubility is high when the medium is acidic. Okay, here we have like gibbsite, it's aluminum-based mineral that's precipitated, unreactive, solid. But in the presence of acidity, it's going to be dissolved into trivalent aluminum, aluminum 3+. That's very toxic to plants, okay? And the problem is that aluminum is the third most abundant element in the soil. It means that if I go acidic, you have soluble aluminum, right? But fortunately, lime is also able to reduce aluminum toxicity by doing this. The same way calcium was able to replace a hydrogen plus in the reserve acidity, it's going to do with aluminum. Aluminum that is in that solid portion of the soil just waiting to attack, right? But calcium is going to do that. It's going to be exchanged with the aluminum, trivalent aluminum, and that aluminum will move to the soil solution to be precipitated by the hydroxyls that were formed with the lime reaction. Okay, now at the very end here in this slide, we are going back to the mineral form, to the gibbsite. So aluminum is no longer, right? One of the problems is that aluminum is it has a negative relation with soil pH, but it's not linear. It's an inverse exponential relationship, okay? That means that after 5, a general value, aluminum is 0, exchangeable aluminum is 0. But any drop in the soil pH, it's going to drastically improve aluminum exchangeability, as you can see in this figure here. And only a small amount of aluminum, like 10 to 30 milligrams, is already enough to reduce crop yields. Like this example here with barley seedlings. So on the right side here, we have pH 4, aluminum 15 ppm, which is on between that range of 10 to 30, okay? So we couldn't see like the root system being developed well. But after lime was applied, aluminum was raised to 5.1. It was not 0, but it was lower than 2 ppm, and you could see the root system developing very, very well. Does it make sense?
Yes, it does make sense.
Okay, good.
Perfect. So how do you determine the lime needs of your soil?
Oh, okay. So we have 2 approaches that are used most part of the time. One of them is called soil pH buffer or buffer pH. Okay, as you can see here, so this is one of the methods. We have like the solid portion of the soil, okay, which is composed of organic matter and minerals. That in that solid portion is where we are gonna have that reserve acidity that I showed you. Okay, when you measure the soil pH in the lab, it's just a measurement of the active acidity, the free hydrogen ions that are free in the soil solution. However, the soil has a reserve acidity, which we call a soil buffer, right? So if the reserve acidity is very, very strong, it's going to replenish the soil solution with more hydrogen and more aluminum if we are targeting only the active acidity, if we're targeting to neutralize only the active acidity, okay? So if you are targeting only the active acidity, only the free hydrogen plus in the soil solution, it's going to be only a short-term goal. Because if the reserve acidity is strong enough, it's going to replenish the soil solution with more hydrogen, with more aluminum, right? So what we want to impact is the reserve acidity, right? So that's a long-term goal. That's why lime is known to be useful in the long term, 3 to 5 years after an application or something. So in your pocket, we will be grateful because lime is expensive, right? So that's how the pH buffer works. We are going to measure the soil pH, okay? And after that, we are going to add the buffer. It's another solution that contains like an alkaline material to attack the soil acidity. Okay, let me exemplify this. Let's pretend this blue line is the blue soil. Okay, the initial pH was 4, and after applying this concentration between 3 and 4 of an alkaline material, the pH was able to raise it to 7. Okay, however, for another soil, let's say the red soil, for that same concentration, okay, with a soil presenting a pH 4, for that same concentration of alkaline material that was being added, the pH was able to raise from 4 to 9, okay? Means this red soil is responding very well to the alkaline addition because the reserve acidity is not as strong as the blue soil, okay? The blue soil is increasing the pH to a lower extent than the red soil because the reserve acidity is stronger. Does it make sense?
Yes.
So the blue soil is going to require more lime to neutralize the soil pH. Okay, so the lower is the buffer pH index in your soil test, the higher is the lime requirement. And that is calibrated, the amount of calcium carbonate you have to apply is calibrated with this soil pH buffer, okay? Mm-hmm. So, and the other one is the base saturation. Let me find the slide about base saturation very quickly here.
So when you're testing for acidity or buffer acidity versus, the active acidity are there certain depths that you have to take samples at to get an accurate picture?
That's going to depend on the philosophy of each stage, on the crops that are being cultivated and everything. What I can tell you is that a general rule of thumb, like for cereal or small grain crops, is 0 to 6 inches or 0 to 15 centimeters. Okay, that's for conventional tillage. When it comes to no-till, since the stratification of acidity is much higher than in conventional tillage systems, it's recommended 0 to 3 inches, because that is where the surface nitrogen application is going to react more. So the acidity is going to be higher in that layer. Okay, so what you can do to overcome this is, since you have to apply lime superficially under no-till system, if you apply for that depth 0 to 3 inches at maximum, it's going to be good because you're going to apply less lime, even considering that the acidity in the topsoil is much higher. That 0 to 3 inches depth of application is going to counterbalance the lime requirement for the high acidity.
Okay.
Does it make sense? Yes. Let me try to show you the base saturation approach. So I would say 0 to 6 inches for winter wheat, spring wheat, corn, soybean. Canola would be, I've seen 0 to 6 inches and 0 to 12 inches as well for canola. And again, for no-till, some people, the maximum they do is 0 to 6 inches. There is no reason to go beyond that, okay? But some studies are now, like in Montana, they're trying to make the recommendation for no-till system based on the 0 to 3 inches.
Okay. So when you're applying lime, there's no tillage required to incorporate it into the soil?
Yes, there are some machines that are, conventional tillage, you can incorporate lime with machinery from the depth that you are collecting the soil sample. You have to make sure you are incorporating lime to the depth we are sampling the soil and getting the test results and everything. But again, that's for conventional tillage. For no-till, you're not going to use machinery, right?
Yeah.
So you just have to superficially apply, yeah. And that's why it's good to apply less lime under no-till, because since it's a surface application, it's going to take even longer to react because you're not incorporating, right? But if you apply less and you are making sure that the topsoil acidity is being neutralized, that's a good approach, I guess.
Okay. So when you're applying lime to no-till fields, because it takes so long to fully incorporate into the soil, is there a concern of, the lime washing away in the rain or something like
that? That depends on the landscape, right? If the rain comes in a flat land, it's going to be better because it's going to incorporate the lime in the soil profile, right? Mm-hmm. But if it did not, but at the same time, under no-till, we have the straw, the crop residues above the soil surface. So it's it's difficult, I think, to lose lime with a rainfall event or erosion because the soil is being physically protected, right? Okay, when you talk about like base saturation, we have to know just a little bit about CEC, or cation exchange capacity, which is like the beneficial or basic cations plus the acidic cations. So since both are cations, either good or bad, they are part of the CEC, right? Because they are cations, right? So base saturation percentage is just like the percentage of the beneficial cations over the CEC, which means the beneficial cations over the beneficial cations plus acidic cations. That's why it's important to know about CEC when you're calculating the base saturation to provide lime recommendation. And what is inside the box? It means that CEC, basic cations plus acidic cations, is calcium plus magnesium plus potassium, sometimes sodium, but not that much. So calcium, magnesium, and potassium, they're macronutrients, right? They are considered basic cations. That's not like the right term for them, okay? But it's just to distinguish from the other terms. That is acidic cations, like hydrogen plus aluminum. Remember, the reserve acidity is composed by acidic cations, and they are part of the CEC. They are part of the cation exchange complex, right? So when we use the base saturation approach, we are trying to be careful not only about the pH, but also about the nutrient balance, the percentage of base cations in the soil CEC. And that is how lime requirement is calculated when you use the base saturation approach. It's the base saturation 2 by 2, I mean the base saturation that you want to achieve, okay, minus the one that you have in the soil, times CEC. That's going to give you how much calcium carbonate you have to apply, either in tons per acre or pounds per acre. That's why it's important to have the CEC value, okay? Because it's going to be used in the calculation of the base saturation that you have in that soil sample that you sent to the lab, okay? While the number 2 is the one that you want to achieve. So just as an example here, there are several ways to determine the soil CEC. I'm just showing you that when I use the base saturation approach to give lime recommendation, it's overall, the lime requirement, it's overall lower than using the pH buffer approach, right? You don't need to understand this terminologies here like CEC total, CEC estimated. No, just trying to show you that when we are using the base saturation approach, it's overall, the lime requirement, it's overall lower than the lime requirement to overcome the pH buffer, to overcome the reserve acidity, right? Of course, that's going to depend on the CEC method you are using to calculate the base saturation and how much you need to improve the base saturation. For example, in a very specific scenario here, like the top graph, we applying lime to raise pH from X to 5.5 is lower than applying lime to raise the base saturation to 95%, okay? But using another CEC estimation, like the orange one right here, even the base saturation to reach 95%, it's going to be lower the lime requirements in comparison to raising the pH to 5.5 and using the pH buffer approach. So, but one question that remains is that how much then I need to improve the base saturation by applying lime? The good thing is that we do not need to increase it too much, okay? So let me show you an example here with soybean in a tropical soil, a very acidic soil. 75% of base saturation was good enough to get the best yields of soybean from 3.5 to 4 tons per hectare. Okay? And that base saturation was related to a pH of 5.5. So that's weird to see it's much lower than the lower end of that good pH range, which is 6.5 to 7, right? So it's something for us to think about. So should I care about the nutrient balance or the soil pH? That is going to depend on a lot of things, right? So anyway, if we are using the base saturation approach, we are somehow increasing the soil pH because we are applying lime anyway, right?
Mm-hmm.
So we don't need to apply too much, maybe we do not need to increase the pH too much. Okay, so from that soybean approach, it seems that you can move it from this to this, right? Because as you can see here, for example, this first pH range for wheat corn 5.5 to 7. Can you see that this range is very broad? If I'm applying lime for the same soil, if I'm applying lime to raise the pH to 5.5, it's going to be a much lower requirement than applying lime to raise the pH to 7, okay? So that's why it's hard to pinpoint pH, okay?
Mm-hmm.
But maybe you can pinpoint base saturation. And one of the justifications is that different soils with the same pH, they're not going to have the same nutrient balance, right? Just as an example, like a brainstorm here, let's say this soil right here is able to provide you 300 ppm of available phosphorus, okay? So that 300 ppm is going to be available in that 6.5 to 7. But do you need that much? And maybe that much it's gonna jeopardize other elements, the equilibrium of other elements by chemical reactions and everything. However, if I move to this side right here, maybe that 300 ppm will drop to 100 ppm. It is still more than the 100% sufficiency level for phosphorus, and it's not going to impacting other nutrients, right? I'm keeping a better balance of nutrients. And also micronutrients, as you can see in the blue line, like iron, copper, manganese, and zinc, they are more available. It's good if I have some deficiency of micronutrients because of high pH, right? So here I can show some studies where the pH actually does not call the shots, like this one here, like using like several winter wheat cultivars that are aluminum resistant or low pH resistant. We can see like the pH threshold is 5.03, okay? So more lime raising the pH to 5.56, 6.57 didn't do anything, okay? Even for cultivars that were not resistant to the soil low pH, except for Gallagher, because Gallagher is very, very sensitive, okay? But for the others, like the maximum pH was like 5.8, okay, as the very last one here. So it's still much lower than that lower end of 6.5, right? But unfortunately, those kind of works, they did not care about the base saturation. How was the base saturation and the nutrient balance at that pH, right? So some works in the past here in Washington and Idaho were showing like threshold pH for maximum yield, like lower than 5.8. Here, lower than 5.2. Other examples here, lower than 5.4. And some like very recent examples, like lower than 5, okay? It doesn't matter if the cultivar was pH resistant or sensitive. Okay, applying more lime, getting higher pHs, it's not going to do anything. Unfortunately, they did not care about the base saturation. How was the balance of nutrients at that pH for that soil, right?
Mm-hmm.
So maybe you can pinpoint base saturation, but it's hard to pinpoint pH.
Mm-hmm.
So just some considerations here when we are comparing base saturation and pH buffer. We can see that base saturation is going to consider the proportions of calcium, magnesium, and potassium on your soil test. Buffer pH, it's going to focus only on the pH level, okay? So with the base saturation, depending on the level of calcium and magnesium that you have in your soil test, you can decide if you're going to go for calcitic lime that raises calcium or dolomitic lime that's richer in magnesium, right? In the other one, you're just going to target just a pH. You're going to apply lime to reach that pH, and maybe you can unbalance calcium and magnesium depending on the lime type you are applying, right? And targeting base saturation, maybe it's going to keep a proper pH for micronutrients, the cationic micronutrients, because they like low pH. And in the other one, if we go like 6.5 to 7, where I already have a micronutrient deficiency, it's going to be even more deficient, right? It seems that utilizing base saturation approach, it's going to save costs because you're going to apply less, okay? But what do we have to do? For example, here I'm talking wheat yields, but actually can be for any crop. You can try to define the best base saturation or best base saturation range if you have several cultivars for crops to decide lime requirement, and then you can establish the optimum, right?
When you're applying lime, are there any nutrients that farmers would typically apply that shouldn't be combined with lime, or does it not really matter?
I think, let's say, like to respond this in an easy way, let's say it doesn't matter because they're gonna apply lime before applying fertilizers, because lime needs time to react to reach a good pH. Then they will make sure that by applying fertilizers before sowing the crop or at the moment they're sowing the crop, it's gonna have a pH that's gonna be favorable to make those nutrients more available, right?
Yeah. So because you have to apply lime so far in advance, when would you recommend it be applied? Like at planting, before planting?
For lime?
Yes.
Lime material, the products, they are going to have different levels of effective calcium carbonate equivalent. Calcium carbonate is the majority of the product, but it's not 100% because the material is not 100% pure. Okay, so what I would say, like for the lime products that you have there outside in the world, a good thing to do, either incorporating or applying superficially low rates under no-till, would be like 3 months before sowing the crop. Okay, but if the particle size is very fine and your effective calcium carbonate equivalent is very high, the reaction is much faster. Then you can go like 30 days before sowing the crop or something.
Okay. So based on the different types of lime that are available,
yeah,
are there some that are more effective than others that you would recommend, or is it just whatever's affordable?
I think whatever is affordable. Like there is liquid lime. I never tested. I don't know the results yet about liquid lime, how deep it goes down the soil profile. But if it's liquid, it's going to react much faster than the solid material, right? But there is liquid lime outside, but that could be recommended with proper tests and more research. There is also other organic amendments that they have like a lime effect, but they are never going to be applied as a lime material. They're going to be applied as a source of nutrients like nitrogen, phosphorus, and potassium. Any lime effect is going to be just a good consequence of the application.
Mm-hmm. Okay.
Yeah.
Is there any way for no-tillers to avoid like stratification issues when applying lime, or is that just kind of par for the course?
Yes. This is one of the things that they are trying to use liquid lime. Mm-hmm. It's because you're going to superficially apply under no-till, and maybe it's going to move down the soil profile much faster than solid lime, and then it's going to avoid stratification, okay? But, I mean, one thing that would be good to see is where the root system of the plants are more active. If it's in the topsoil, the uppermost soil layers, where the acidity under no-till is much higher, then applying lime to react in that layer would be enough, right? Mm-hmm. But to avoid stratification, but just like a brainstorm on some assumptions that I have, okay, it's to combine the lime application with gypsum. Why? Because we apply lime first. It's going to react on the soil surface, okay? It's going to cause stratification, high pH now in the topsoil because we applied lime. And then sometime later, we can come with gypsum. Gypsum is much more soluble. It's going to move down the soil profile because lime reacted first in the topsoil. So gypsum will move down the soil profile to try to overcome some of the acidity indirectly in the subsoil. That way we can avoid some stratification, okay?
Is there anything else that you would recommend no-tillers to do when they're applying lime this year or next year?
So, but to answer your question first, so I would tell them, I mean, if they're under no-till for long term, apply nitrogen superficially, I would try to analyze the soil from 0 to 3 inches. Okay, the acidity it's going to be much higher than if they are analyzing the soil from 0 to 6 inches, for example, because 0 to 6 inches would dilute the acidification in the topsoil. And they're going to tell me, but if I'm going to, for the topsoil, the acidity is going to be much higher. It means that I'm going to apply more lime. No, you're going to apply less lime because you're going to try to remediate that layer. And that smaller layer, okay, less deep layer, applying based on that portion of the soil is going to counterbalance the high acidity in the topsoil. I'm going to show you a graph that I have about this. Can you see no-till there?
Yes.
So can you see that we have like stratification, like from 0 to 20 inches? We have soil pH much lower in the topsoil in comparison to the subsoil. Can you see that?
Yes.
So let's do a test, okay? Let's calculate. Let's see. Focus on the right top graph, okay? Where on the y-axis you can select the buffer pH, right? Can you see that the buffer pH for from 0 to 2.5 centimeters is overall lower than from 0 to 15 centimeters, mainly for the highest rates of nitrogen application? Can you see that?
Mm-hmm.
So remember, if the buffer index is lower, means that I'm going to have to apply more lime because the pH is not increasing too much from an alkaline solution that I'm applying to the soil, right? It means that the reserve acidity is very high, okay? So from this graph, you can tell me, okay, so my buffer index is lower if I sample from 0 to 2.5 centimeters than if I sample from 0 to 15 centimeters. So it means that I'm going to have to apply more lime. No, no, if we are focusing on that layer, the amount of lime to act on that layer is going to be much lower, even if your topsoil acidity is much higher. Can you see here? That's the graph in the bottom.
Mhm.
That's the effective calcium carbonate equivalent that's necessary to neutralize acidity, that layer, in comparison to 0 to 15 centimeters. So here is 0 to 1 inch. It's not 0 to 3 inch. But even if it was 0 to 3 inch, it was going to be lower, because can you see how much lower it is in comparison to the 0 to 15? So the message here is that definitely specific lime application is going to counterbalance high topsoil acidity. It means even if your topsoil acidity is much higher, you are going to apply less lime because you're going to be restricted to that layer. Does it make sense?
Yes.
Okay. And the last thing that I'd like to show you is why sometimes we do not see response to pH increase under no-till sometimes, okay? Here is just to show you like organic carbon under no-till, as the blue line you can see is much higher in the topsoil than in the subsoil, right? Or if we are taking samples from the uppermost soil layers in comparison to the arable layer, right?
Mhm.
It's organic carbon, and it's most part of the time higher than in the topsoil than if you sample from 0 to 20 centimeters, right?
Mhm.
So what happens sometimes is since lime is superficially applied under no-till, maybe it's not going to respond to the increased pH because aluminum can also be complexed by dissolved organic carbon. Okay, for example, in the 0 to 20, in the 0 to, in like the blue graph here on the right side, at pH 5.1, for that soil layer, 0 to 5 centimeters or 0 to 2 inches, aluminum is 0 at pH 5.1 because it was being complexed by dissolved organic carbon. So it's being much more effective, the no-till itself, than the lime application. The other hand, the 0 to 20 centimeters where I cannot get that much of organic carbon in my soil sample, right? Because it's being diluted by the tall between cold soil layer. I have at the same pH aluminum at 26 ppm. Does it make sense?
Mhm.
Yeah. So sometimes we can rely on no-till to neutralize aluminum by forming aluminum dissolved organic carbon complexes. And in that case, lime is not going to do anything because aluminum is already being precipitated by dissolved organic carbon from the no-till practices. But that's going to depend too much on the mineralization ratios of the organic matter you have under no-till, how long you are cultivating under no-till, which crop residues you are having, and everything. So all of these open studies for research, right?
How much lime typically do you see farmers purchasing, or no-tillers specifically?
I don't have that information yet. I'm sorry. I'm gonna know that information better because I'm gonna to attend some meetings this month and the next month. I do not know exactly how much they are purchasing, but I can tell you that for those that are applying, okay, either conventional tillage or no-till, they are applying on average 2 to 3 tons per hectare.
Okay.
But how much they are purchasing, I don't know. One of the problems here in Washington is that the transportation is a huge part of the cost to bring line here for them to apply. That's a huge part of their cost. In addition, lime is an expensive material. So we are having now, currently, some companies that are trying to find some limestone deposits to create those products here to make it cheaper for farmers.